So with the assumptions that we've stated in the previous video, we now want to prove the following lemma. I times the integral over all space of e to the power I kx, where kx is the 4 dot product, the wave operator acting on the Heisenberg picture quantum field is equal to the annihilation operator at time plus infinity minus the annihilation operator at time minus infinity. This is what we want to prove. So here's the proof. So we assume that the field operator phi of x dies off as we go to spatial infinity. Now this is consistent with the assumptions that we usually make, that our quantum fields die off at spatial as well as temporal infinity. So of course we are going to take the time limit here to be very carefully, but for the time being we can start with this assumption. So with this assumption we can then write I times d4 of x e to the power I kx del squared x plus m squared acting on phi of x. Now what we're going to do is that we are going to decompose this D'Alembert operator in terms of the time derivative part and the Laplacian part. So we can write this as I times integral over d4 x e to the power I k of x, and now this can be written as d squared t minus the Laplacian plus m squared acting on phi of x. So next what we do is that we do a integration by parts. So on the spatial integral, so just consider del squared of phi, and we are doing an integration by parts, so there's an integral sign. So we can write this as the divergence of e to the power I kx, and then the gradient of phi of x, and then we'll have a term which is minus the gradient of e to the power I kx dotted with the gradient of phi of x. Now see that this term is going to be a total derivative term, and therefore if we have a spatial integral on this thing, so we are now adding an integral over all space, then the first term can be written as a surface term on the boundary of our space. So if our space is sigma, then we are writing this as a boundary, and that will be dotted with the gradient of phi of x, and then there's also e to the power I kx. So this is going to be the first term, and the second term is going to be, since the second term is not a total derivative, it's just going to be minus d cubed x, but this gradient acting on this will just bring down a factor of I, three-dimensional k, and then we have e to the power I kx dotted with the gradient of phi of x. Now we have written this as a surface integral using Gauss's divergence theorem. Now see that this is, because this is at the boundary of our space, we are evaluating the field where the x is going to infinity. And therefore, by our assumption, this is going to be 0. So the boundary term drops out, and we have just this term with I times k replacing the derivative operator. But since we have two derivative operators here, we can do this exercise twice. And if you do this, then what happens is that this term, this factor, gets replaced by minus 3-dimensional k squared. And this minus gives us a plus sign, and therefore we end up with I times d4 of x e to the power I, k times x, the time derivative squared, and then we have plus 3-dimensional k squared plus m squared, and then phi of x. But this is nothing but the energy squared, the relativistic energy squared. So we can write this as d4x e to the power I kx del squared t plus ek squared phi of x. Now, what we want to show is that we want to rewrite this in a different form. To do that, let's consider the time derivative of e to the power I kx times I, the time derivative, plus e of k, and then phi of x. So what we then do is that we can apply the time derivative, and the time derivative will act on this guy, and when it acts on this guy, what do we get? We get I times e of k, and then we have e to the power I, k of x, then I times del t plus ek phi of x. And then the second term, this guy will act on the rest of it. And if it acts on the rest of it, then the first term becomes I del t squared. And the second term then becomes e of k times derivative with respect to t phi of x. And let us not forget there's e to the power I kx in the front. Now we can just write everything out. Then the first term, we see that there's an I here, there's an I here. So those two i's give me a minus sign. And then I have e to the power I kx, then e of k, and then the time derivative of phi of x. And then the second term is plus I e to the power I kx e of k squared phi of x. And then the third term is e to the power I kx I del squared of t acting on phi of x. And the fourth term is plus e to the power I kx e of k, the time derivative of phi of x. And here we see that the first term and the fourth term, they cancel out, leaving behind I e to the power I kx, and then inside the bracket we get del squared of t phi of x plus ek squared phi of x. And this is something that we recognize as the integrand in our expression above. So our expression was I times d4 of x e to the power I kx del squared of x plus m squared phi of x. and that's going to be equal to, what we do is that d for x e to the power I kx dt squared plus ek squared phi of x. Furthermore, we have shown that we can write this in the following way. Integral over d for x the time derivative of e to the power I kx I times the time derivative plus e of k acting on phi of x. And now what we see here is that we have here a total derivative, a total time derivative. So we can rewrite this expression as the integral over time from minus infinity to plus infinity dt d by dt, and then inside the integral we can have e to the power I ek of t. This is just the time part of this exponential. And then we have d cubed x, which is the spatial integral. And then we can write the spatial part of that exponential over here. And then we have the rest of the stuff as it was. So we can now do the time integral because it's a total integral, so it's trivial to do. So we will get e to the power I ekt, the integral over all space, e to the power minus I, three-dimensional k dot three-dimensional x times I, the time derivative, plus e of k acting on phi of x, and the whole thing is evaluated from t plus infinity minus t minus infinity. Now let's look at this thing at times plus infinity and minus infinity. Now, because at time plus infinity and minus infinity, we know that the creation and the annihilation operator say a of k at say minus infinity and or dagger and a of k at plus infinity so all of this thing at those times become independent of time. And that's because we're assuming that the interactions turn off asymptotically, and therefore the creation operator and the annihilation operators asymptote to their free versions. So we're going to use this in evaluating this expression, because this expression needs to be evaluated at the asymptotic times. So let's go and do that. So first we have e to the power I ek of t, and then we have d3 of x e to the power minus I k dot x, and then what we have is I del t plus e of k, and then for phi of x we can write d cubed of k prime divided by 2 pi cubed 2 of ek prime, and then here we have a of k prime at time t e to the power minus I k prime x plus a dagger of k prime t e to the power plus I k prime x. So now what we do is that we just use this time operator keeping in mind that we are evaluating this expression asymptotically, so that the time dependence of the A operators drop out, and therefore the derivative operator will not act on these guys. So if I assume that, then I get e to the power I ek of t, and then for the integral I have d cubed of k prime, d cubed of x divided by 2 pi cubed 2 of e of k prime, and then I have e to the power minus I k dot x, so this is a three-dimensional x, and then here we have this thing acting on this will bring down minus I ek prime, but this minus I and I will give me plus of ek prime, and then there was already a plus of ek, so we get a plus of ek, so this is what we get, and then we also have a of k prime times t of t e to the power minus I k prime x. And from the second term, what we get is that because there's a dagger here and there's a plus sign here, I get plus ik prime, and the plus I gives me minus e of k prime plus e of k, and then I have a dagger of k prime of t e to the power plus I k prime x, right? So we can write this in a slightly different form. See that factor here? We can just move that factor inside over here. So here, and because there are two terms, we have to. We should copy this. Sorry. Right. So this is what we get. And next, what we do is that here we've got a couple of delta functions, and we can do the x integral. X integral, which will generate a delta function because we have exponentials in there. So we have d cubed k prime divided by 2 pi cubed. If we do the d cubed x integral, then in the first term, we are going to generate 2 pi cubed del cubed of k prime minus of k, and then we are going to have e of k prime plus e of k divided by 2 of ek prime, and then we'll get a of k prime of t, and we'll have left over e to the power minus I e of k prime of t. And in the second term, we'll have 2 pi cubed, and we'll have del cubed, and see here sign, the spatial part of this guy will have a minus sign, this has a minus sign, so both has a minus sign, so the delta function argand will be k prime plus k. And then we'll have here minus of ek prime plus ek divided by 2 of ek prime. And then we'll have multiplying this a dagger of k prime of t e to the power plus I of ek prime of t. Now, if I do the d cubed k integral, so putting all of this together, we get the prefactor e to the power minus I ekt, and then the second term here vanishes. Therefore, we have from the first term a k of t, and then we have e to the power plus I, e of k of t. Of course, these two things cancel out. So as a result, we have shown that I d4x e to the power I kx del squared x plus m squared phi of x is equal to ak at plus infinity minus ak at minus infinity. Of course, if we take the Hermitian conjugate of this, we're just going to get I d4x, there's a minus sign here, so we get e to the power minus I kx del squared x plus m squared. We're dealing with a real scalar field, so that's not going to change anything. And here we are just going to get ak of dagger plus infinity minus a of k at minus infinity with dagger. And we can change these signs and get the signs changed here.